welcome to Ladyada.
Hey everybody, welcome to another desk of Ladyada. This is a post-Superb Owl desk from stuff I was working on yesterday, actually.
We'll show an owl at the end of the desk of Ladyada that we're doing.
There will be an owl, so stay tuned for a real live owl, or the somewhat live owl. So today's topic is still capacitive touch, but now we're going to be talking about QTouch. And is
that like a Q-tip?
It's like for Quantum, I think was the name of the company or something. Anyways, it's basically capacitive touch. You know, as you showed, you can use a resistor and a capacitor. A resistor and two pins, and basically it's pretty easy to use that to see how long it takes for a pin to decay after it's been charged through a resistor, and that works pretty well. And in fact, that's how we have historically done capacitive touch on the circuit playground. So let's go look at the computer. So this is the circuit playground, and if you look in the schematic for both the express and non-express version, there's basically these resistors, 1 mega ohm resistors that go from all these analog input pins. They have to be analog inputs. Well, they don't have to be, but it helps, it makes it a little bit more efficient. And they go to another pin. In this case, it's D29, which is my capacitor push pin, and that's the pin that I use to toggle. So the good news is that this has worked quite well. We've used it in the Circuit Playground Classic. It works fine on the Express. It works on any microcontroller, really, because it's just digital pin high, pin low. You can even just use the digital read capability of any digital pin. So it's very easy to add capacitive touch to it. You know, it doesn't calibrate. It's not terribly fast, but it does work. And these here, this here is the resistor pack. So this is a 4 resistor pack, and it's the size of a single, 1206 resistor, but it has, 4 resistors in it. It's faster to pick and place. They're a teeny bit more expensive, but I prefer them. Here's the other one. So this one goes to, this pin, that pin, that pin, that pin. So these 4 pads are handled by this resistor pack. And then these 4 pads are handled with this resistor pack. So, it's effective and it's worked out quite well. But one of the things that was kind of neat about this SAMD processor, wasn't the reason I picked it, but it was a nice extra, is this chip, in theory, has let me find where it's mentioned here. It has support for capacitive touch buttons. Natively. Hold on, move this over. It has support for capacitive touch because, I guess they licensed the technology, they bought the technology from some company. It was merged, and again, I think his name was Quantum or something. That's why it's called QTouch. And it's called the Peripheral Touch Controller. And so you can have an XY grid, you can have individual buttons. And what's nice is that, first off, you don't need those resistors, and you don't need another pin. And the nice thing about that, the bad thing about having those resistors is all the pins are kind of tied together, even though it's a 1 mega ohm resistor, so it's like 2 1 mega ohm resistors. There is a little bit of, each pin is kind of connected to every other pin, which is not as much fun and can cause some interference issues, especially if you're fighting against some other sensor signal that's not very strong. So being able to use the peripheral touch controller would be really nice because it would save me those 2 resistor packs, a little bit of money, a lot of space, which I'd like because I want to put some more parts on the board. I'd rather have fun sensors than resistors. Okay, so what's really nice about Atmel datasheets is wow, there's just so much information and it's so helpful. And you're oh, I want to do circoms and what's the dependencies and the functional descriptions and it tells you interrupts and events and it's so awesome. And there's register summaries. It's wow, the full register map of everything. Isn't that great? So then you get all the way to the bottom and you're ooh, peripheral touch controller. And you go here and there's absolutely no information whatsoever. At all. I hate this. I hate when this happens, but it happens. So this is kind of a jerky move, but it doesn't mean I'm not going to say no to this chip. But basically, instead of actually giving you the register map, which is not that many registers anyways, and telling you how to interact with this hardware peripheral, they say, oh no, you have to use this library. There's actually like literally a binary that they give you, and you link against this library, and you call like capacitive touch init, capacitive touch read. And I asked them like, hey, can you open source it? And they're like, no, and there's a really good reason. And I'm like, yeah, I'm sure the reason is like top notch. So that's not going to happen. But the good news is, well, first off, I don't need to use this peripheral. So if it doesn't work out long term, it's okay. But it would be really nice if I could. And so I was like, well, let's look at, what's going on when I run the example code and see if I can figure out what's going on. Because the good news is, like we showed with the last few Desk of Ladyas where we talked about capacitive touch, it isn't that complicated. Like you can do a lot of filtering and you can do like oversampling, but overall the basic idea is like, you have a resistor, something's charging, your body capacitance changes it, you read that value, and you've got your value, and then you just do some filtering, and there's a threshold, whatever. So if you want to use the PTC, Peripheral Touch Controller, you would use something like ML Studio. Now we actually Scott got this linked in. He basically linked into this library and calls it for CircuitPython. So in CircuitPython, we do link to it. The problem is that we're going to have to eventually take it out because it's like 16K of flash, and we actually can't spare that much flash memory. So it's not like oh my God, if I don't get this done, we won't have capacitive touch. But like kind of, if I want to have capacitive touch in Python, especially for the smaller boards, which don't have external SPI flash, I'm going to have to get this working. So whatever, hopefully I can get this working. So I'll just show how you make a project with it to show you kind of the process. So let me close this solution. Yeah, I'm going to stop debugging. And you create a new project, and then you say, it's a special type of project because it'll give you all the links and everything, and it'll kind of structure it for you, because they're kind of like, I think they realize like, oh, it's kind of shitty not to give you like example code, so they make it easy for you to make a project. And then you say, what kind you want. You want like a library project. And then you can like select how many buttons and like, which pins they're connected to, and it'll then generate the code for you. And it has all the chips that are supported. It's funny actually, the Atmega 328PB, which is the upgrade of the Atmega 328P, also supports this QTouch library. So yeah, it's kind of interesting. They've started to put it into almost all the chips. You can see like all the SAMDs have it. Even like the SAMD 10, which is a very inexpensive, it's like a 40-cent chip, they put in the Peripheral Touch Controller. Anyways, so once you do that, you basically get a project that looks like this, where you have a main, and you end up calling into that linked library object. It's like QTouch.a or something. And if you look around, like there's header files, but of course they don't have any register information. And basically sets up some timers, and then sets up some clocks, which is not so interesting. Basically you call touch sensors init, and if you go to that, it's in here. And it's, it calls functions called like touch sensor, self-cap sensors measure, and touch self-cap sensors calibrate. So all of these functions, this touch self-cap sensors calibrate, I have no idea what's in that code. Okay, I wish I knew, but I don't. And like touch sensors config, I'd like to go to the implementation, but I can't. So some of these things they do tell you. They basically tell you how to configure the clock, because you probably do have to change the clock, depending on how you're clocking your chip. If you're running at 48 megahertz or not, you'd have to tweak that. But everything after that is locked away. But let's just try running this and see what happens. So I'm not that good at Visual Studio. So I know people are going to be watching and being like, you're not using it right. Yeah, I know I'm not using it right. This is like the third time I'm using it. So I can start debugging, and can we go to the overhead? So I'm doing this with an Arduino Zero, because the Arduino Zero, it has this eDebug chip, And this chip is natively supported by Atmel Studio, so you can use this chip in debug mode. Otherwise, you have to use your J-Link, which I have, but it's like, this is kind of nice because like we stock these in the store and it's like $50 or something, so it's like very easy to debug, and it's a chip that's supported natively. Like it's all set up very easily to use natively inside of Atmel Studio. So like, can you jig this up yourself with like a feather and like a J-Link? Yeah, you can, but I had these handy. And while it's debugging, you see this blink light. And then I have the oscilloscope hooked up to pin A0. So pin A0 is actually, can we go to the computer? So I'll just show really quickly. Not every pin can do capacitive touch. If you go to there's the Y lines, Y15 through Y0. These are the pins that can do external single capacitive touch. Like use XY matrix, but the Y ones can be individual. So PA2 is the same as Y0. So this is one of the PTC supported. Only these 16 pins are supported for individual touch. Anyways, okay, so it's just the easiest because it's like Y0. It's just, the first pin. Okay, so can we go to the scope? So this is the default that comes out of the pin. So at least like something's happening, right? And it looks kind of like, well, something's going on here. There is a, it looks like over here it's kind of dropping down. But this isn't, I think, what's measuring it, because by default, it's like, it oversamples 16 times. And so you can count if you wanted to, 1, 2, 3, 4, 5. There's 16 of these like N pulses, up, down. And then in the middle, it actually sits in between the two rails. And then when I put my hand on the pin, I'm actually kind of getting the triggering. Great. Hold on. That's annoying. Well, you can still kind of see. It goes from being, a nice, like, ziggurat look into, you see it kind of it curves, and that middle part where it's normally in between the two rails, it takes a little bit of time for it to charge up and then discharge from that voltage. So I think that's what it's measuring, right? Like, what voltage does it end up at, or like how long does it take to get to some analog reading? Because you can tell it's doing this measurement multiple times. And then, you can verify that by, even though we can't get into this binary code, there's things you can do to kind of like, figure out what's going on here. So, for example, let's go back to the computer. So in touch.h, you can set up all the different things, like how many channels. For now, I actually just want to keep it to one, because I want to only do one channel at a time, and you'll see how later on you'll add multiple channels. But starting with one is kind of a good idea. So for example, def self-cap filter level per node. This controls the number of samples taken. Okay, so like if I change this to 1, because you can have a different filter level, I'll save this, and then we compile and run it. Then when you go to the oscilloscope cam again, you'll see now I only get one of those pulses. So that's clearly occurring through like the hardware, and it's like that at least I know, like, okay, that definition affects this. So the question is, how much of the library is library code and how much of it's hardware? Because if I were a hardware engineer, so one of the good things about reverse engineering is, unless you're reverse engineering game copy protection, you can kind of use like an Occam's razor, like usually, where the most obvious thing you'd think it would do is the thing it does, right? Like, if you want to check out like some hilarious reverse engineering of video game protection, check out the 4 a.m. It's like 4 a.m. as in like you're up really late. He has a Twitter account. I think it's a he. Well, they have a Twitter account, and they post these text files of reverse engineering Apple II games to crack them so you can play them again, because like nobody has an Apple II anymore. And like Burger Time, which was like not even such a great game, there was just like 18 layers of copy protection. Like nothing was as it seemed, because everything was meant to keep you from playing this game. However, when you're talking about microcontroller code, you know, people can make mistakes, but they're not usually, unless they're trying to protect something on purpose, they're not usually obfuscating, right? Like usually it's like, well, what, you know, you want to draw to the screen, you're just going to draw to the screen. You're not going to like do like a function pointer to something that like self-modifies the code. You're not going to do that because it makes it harder for the developers. They're going to have just a function that points to the screen. So with this stuff, you know, my thinking as like a hardware engineer, how would I design the capacitive touch library? Well, you know, this waveform is not a normal waveform. Like this is really weird. You know, like digital microcontrollers to go high or low. Like this is weird to have something in between. And clearly there's like some analog reads. So this pulse form and the sampling that occurs at this point, I believe, is done in hardware, right? There's a little like op amp or there's some comparators or something going on. There's a little chunk of digital logic that does this. But the auto calibration and like managing, you know, like cross talk, that is probably not going to be done in hardware. That will be done in software, right? You want to offload as much as you can to software, because hardware is really expensive if you get it wrong. Like if you screw up this, like you put in like the wrong values or something, or you don't trim your resistors right, it can cost millions of dollars to get your mask fixed. Well, maybe not millions. You can usually patch it up a little bit, but it's still going to be very expensive and annoying. And you don't want to put like your capacitive touch calibration here, because what if the needs of people's capacitive touch changes? Turns out, you know, like people are no longer using glass for capacitive touch. They're using now like a new material, and you have to start, calibration is completely different. The thresholds are different. You don't want to have that stuck in hardware. You want to do that in software. So the good news is probably all I have to do is get this pulse generated and then get it to read that, you know, that value as it goes up and down, figure out how to get that value. And I'll just do the manipulation myself, right? So hopefully. This started on this like yesterday night, so we'll see how it goes. It also, I might not succeed at all. Isn't that the joy? So the good news about some of this stuff is, well, you know, I was like looking at the data sheet, and they did give you one hint. I was like, one hint. If you go to the PTC, can you go to the computer? If you go to the PTC here, it kind of just show you like, okay, there's some resistor you change, and then there's this compensation circuit, and then there's different, you know, this stuff maybe is kind of hardware-y, but then, and it sends you an IRQ, but the actual, like the gain control, yes, like how much, you know, you the gain of like reading or like changing this resistor value, that will happen in hardware. So all I have to do is figure out how to poke at those things. So the good news is somewhere here, I think it was in the memories, they do tell you, okay, well, you know, the memory, because they usually give you the register map for like where you want to do it. No, I actually remember it. It's 4C00, 4200. Maybe it's 4200, 4C00. Yeah. It's in the peripheral configuration summary. They do tell you, well, this is the address right above I2S and below the DAC. This is the address for the PTC block. This is where all of your registers are going to happen. This is where the magic occurs. So, in theory, I just kind of have to like look at what's going on in this zone while this code's running, and like hopefully there'll be some information. So, I'm basically doing a two-pronged approach at this because I don't really know how to do reverse engineering. So I'm going to try a bunch of things and I'm going to throw them on the wall and see what happens. So the first thing I'm going to do is I'm going to stop, well, not here. I'm going to stop at this point. So let me insert a breakpoint. Oh, man, stop. Okay. So I'm going to insert a breakpoint right after touch sensors and knit, because although, you know, I could go into here and it would be like right after this point, this touch sensors config. So maybe I'll stop right here. We'll see how that goes. Although sometimes it doesn't seem to stop at the breakpoints, which is a little annoying. So while that's happening, so let me just run. Let's see where I end up. Okay. So I just finished the config. Oh, and I already had this up and running. So you can look at the memory location, which is really nice about debugging. And I can say, hey, debugger, give me a look at the memory at this location. So, hold on, let me stop. Let me start here. Okay. So this is what happens before, I believe this is before the config occurs. So we can look here and we see this is the memory location. I'll actually change this to be 4-byte integers and then maybe 2 columns. So this is, so this is individual registers, and you see all the way down. And we'll start with, this is the base register. So basically everything from here down is stuff that's modified by the PTC peripheral. Now there's other like pin muxes and stuff, but I can figure those out. Like that's well documented. Like you put the pin into the PTC mode. So let's continue. This is what I don't understand. It like doesn't stop at the next stop thing. So let's try that again. Again, I gotta figure out this. If you stop after it's done initializing and configuring, you'll see there's a lot more data point. Like there's a lot more data. Like this register is set to 6, and then like this register is set to like 100 is in hex, and then this one is set to 4. So what's interesting is like, okay, so we have like some data here. What I'm going to do is I'm going to take this, and this is like not the right way to do it, but I'm going to do this for now. I'm just going to put it into a text editor. If I was doing organized, you'd like have an Excel spreadsheet and stuff. But what I want to figure out now is what of these, this is just the configuration. This is like step 1. This is just the configuration. Which of these pins, sorry, which one of these bits means what?
Do you want to answer any questions?
One more second.
Yeah.
I'm going to do one thing and then I'm going to stop because I'm going to wrap up. So for example, let's say I want to change which is the capacitive line. Like so by default I had it be A0. What if I set it to be like A1, like the Y1 pin, and I want to see what changes when I recompile the code and run this, because somewhere in those registers it's telling me which line to look at. So if I can figure out which one those are, I can remove them. Like I can start mapping out the registers. So this time I ran it again, and when I stopped right after initialization, this is what it looked like. So now when I paste this down here, and you can actually see there are some differences. So this 6 here is the same here. And this 100 is the same here. Usually the first couple registers in a peripheral are like configuration and like which clock to use. So like that's not surprising. This 4 hasn't changed, but this 1 has changed to a 2. And actually this 1 has also changed to a 2. So that tells me that this register here, I already know now the first 16 bits of that register are like guaranteed going to be telling you which line you're connecting to. So that's kind of good. Right now I only have one channel. It could be that if you have multiple channels, each channel is going to have its own 16 bits. So the fact that this is kind of empty here might mean like, oh, if you have multiple channels, so like what I would do next is make a new project with like 8 channels and see which bits light up when I do those. So then the next question is like, okay, well, what's another attack vector? Well, what's the question?
Okay, the question is, if those are registers, could the act of reading them have side effects?
Yeah, they can, but usually not unless, the only time it really, well, not from the debugger. So the debugger, I believe, does not affect the reading, not the way you would if you were reading it from your own microcontroller program, because it's doing it through a different interface. When you have like interrupt bits, sometimes reading them does clear them. Although I don't remember if the SAMD chip does that. So I'd have to, what I would actually look at, actually Scott had a suggestion, he said, well, you should look at the other peripherals and see like what their pin mapping is, because that will help you, sorry, what the bit mapping is, because sometimes they kind of like reuse the same structure for registers. Like, I'll show later, like I found one bit through a different method, and he's like, oh yeah, like the second bit is always this. I'm like, yeah, like, but this is a good way of figuring it out. Was there another question?
That's it.
Okay. So then, you can do this, and you can actually, you basically have a spreadsheet, and you could start mapping out the registers. Then what you can do is, instead of stopping after configuration, you could stop after a read. So let's run until we do a read. And actually, what I want is I want to stop after the read. Hold on, let me, still learning how to use this. Okay, so after measure, actually let me stop here. I think that's where I stopped. No, I was actually getting data last time I ran this, but I also might be stopping at the wrong point. Another thing is this, this example uses a timer, and I actually have to like rewrite it to remove the timer because it's a little annoying. Yeah, it doesn't actually have, it was before I was actually getting it too. There was a couple of like, it looked like, binary data was appearing here. So there's another way you can do this, and that's using like a disassembler decompiler. So the nice thing is we have this code. So even though it's in a binary format, there are some symbols that are available that can help. And another nice thing is, as assembly goes, ARM assembly is pretty easy to like read. Like there's not many instructions, and like they have like very well defined performance. So I actually tried a couple, and the only one that could do a pretty good job was IDA, which is commercial. So I'm probably going to buy it because it would be totally worth it if it helps me with this project. And I will open up Qt1, and you would open up the ELF file, which also has some debugging information. And the type of file is ARM little endian. To find out which endian you would look in the data sheet, and like, if you search it. This one is a little endian. And it needs to be able to do like thumb disassembly, which this one did correctly, and most seem not to be able to. I tried a couple online ones, and like I could pretty clearly tell that they weren't doing the right work, and then I kind of just did the defaults. What's kind of nice is it gives you, for assembly only, it gives you like pretty good information about what's going on. So for example, let's go to, this is actually the first one I looked at, and turned out I was like, well, this is pretty simple. If you go to, well, what's really cool is a lot of the functions that aren't used, like you don't call them, they weren't declared static or whatever in the library, and so the names are exposed, which is kind of nice. So you can actually see like, this is kind of cool, like there is a function called frequency hop tune process. So that's kind of nice because it means that if you want to do the frequency hop tune process, like you know this is the function that does it. Again, it's a little bit of Occam's razor. If the function is called PTC in its settings, it's going to do PTC in its settings. And what's neat is, for example, you can go to functions like disable PTC, or actually more useful is enable PTC. This is not.
Did you want some comments from the chat as you do this?
Well, let me just do one more thing. This is
Okay.
very fast, and I'm going to be done. I just have this is not alphabetical, so I have to find where. Enable PTC. So enable PTC. I mean, what does it do? It probably enables the PTC, right? So what's neat is this is almost like human readable, despite being like assembly code. You only need to know a couple little details of how the instructions are named. So push just, it pushes stuff onto the stack. You have to worry about that. It calls a function called syncconfig, and you can jump to it. But if you've ever done anything with this chip, you know that you have to synchronize the register. It's a very generic process where you basically tell the chip, hey, synchronize all the buses because I'm about to do stuff to a peripheral, and I want to make sure that nothing is going on. It then moves the value 2 into register 1, and then it moves the value 42004C00 into register 2. Now, what does this look like? That's that register address, right? That's the first register in the PTC register setup. And then you LDRB. This basically says, and these brackets are kind of tell you what it's doing. It's a referencing. It's saying get the data out of what's in R2. So basically, look up that register, grab the data, or RS, or that data, R3 with R1. So turn on the second bit, and then store it back into R2's location. So read the data from this register, turn on the second bit, write it back, enable PTC. Now you know for sure that that address location, that second bit, you know exactly what it does. So luckily, those two are pretty simple. Disable PTC is the exact same thing. Fortunately, these are the only two really simple ones. The rest of them are a little bit more complicated. So, but it is, it's not like impossible, just so you go through each one. And I don't need to completely understand everything that's going on. I just kind of get hints about what's going on with all these registers. If I can kind of map up which register is register I have to hit to say start the, because the configuration, I know what my configuration is. I can, to configure the registers is very easy because I can make that project, look at the registers, steal those register values and write them. The question is, how do I kick off a PTC, read, like that, getting it to that waveform, and then how do I get it to send me back the data? So hopefully I'll be able to figure that out. What's the comments?
Okay. Just some observations / questions, sort of. So the first one is because the whole block repeats, it may have the same structure for the Y and X sides. That's a question mark.
Well, the X and Y sides are different. So the Y sides can be self-capacitive. The X side cannot be. The X side is only used for grid. So if you're using a grid for a surface. So, and that's a lot more complicated. So the good news is that a huge chunk of the registers are probably used for XY configuration. So just because a huge number of them are going to be 0 it's not a bad thing. It means I'm just not touching the ones that have to do with the grid, because that's a lot more complicated. You need more hardware help because you have to start, you have to correlate multiple points together, whereas with self-capacitance, it's just you're doing one reading.
Okay. And the name of this app is IDA?
This is IDA.
Yeah.
And it's not, I'm using the free version. I'll buy a copy if I end up using it to do this, because it's pretty handy, and also you can take notes and stuff. It's a couple $100, which is why you should support us if you can, so you can pay for people's software. But it's the only one so I tried a couple others and they didn't, and I specifically said, okay, show me the enable and disable PTC functions. And this is the only one that that was smart enough to realize that it was, that register was 32 bits long. Every other one didn't get the register number right. And that's really valuable. That was the most valuable thing, because all I really need are those registers. If I see a function called calibrate PTC, and there's all this stuff, but there's only one spot which it writes a value to a register. I just need that register value and what pin it's setting. Do you know what I mean? I don't need to know the logic behind how it does calibration. I just need to know what bit does it set on that register, or when it says start measurement. I only need to know what is that bit that it's writing.
Yeah. Shout out in the chat, Mike is here.
Yay!
Yeah. Well, someone was, so I guess I was watching the same, but you and I were watching the same video on Friday of Micah doing some reverse engineering. So someone in the chat just said, oh, I really like watching Micah's reverse engineering. I said,
this is baby's first reverse engineering. I've never really done this stuff.
I said, Micah's channel is our favorite, and then Micah was watching. So, anyways,
I could use
reverse engineering's fun.
This is fun.
Yeah.
It's a little time consuming, but hopefully it isn't too bad. I was doing
that program is pretty amazing that it just maps it out.
This program is pretty cool. I'm pretty tempted to get the decompiler as well, because I have such a limited amount of time to work on this, and it's worth so much for me to get this working, because all of the SAMD chips, I can use it in MicroPython, I can use it in PXT, I can be able to use it in Arduino. It's, I think, in the community, right now, you can't link external libraries in Arduino, and they flat out refuse to allow it. So having this reverse engineered would be so beneficial to the community. It's
for
I
all
should make
sorts
sure
of debugging and stuff.
and look, arm thumb is everywhere. And, you know, this is handy. What's funny is when I was in college, I wrote a disassembler, and I was started to write a decompiler, but it's been, you know, I don't have, like, that is a project, right?
So you're using the free version of IDA. What's the version number?
This is just whatever I just downloaded today.
Yeah, can you go to, like, about?
Help, about program.
Yeah.
This is 695, something. Oops, let me turn off Flux.
It's not Ada, it's Ida.
It's, yeah, it looks like Ada.
Yeah.
And this is not the only one. This is just the one, like,
So
look,
it's
I'm on Windows.
hex-raise.com
Yeah.
is the company that makes this.
Um,
It's time limited and saves disabled for the free version.
what I might do, you know, what I might do after I, like, play with this and get it working is I might try to learn Radar, because Radar is really cool. But it's like, it's another 10 hours for me to learn that. And I kind of was like yes, last night I was like, well, I just want to, like, mess around while people are looking at super vowels. And, but what's really neat is it's like all my MIPS assembly, like, is coming back to me. I'm like, oh yeah, that's right. Like, it's move and the S means store, you know. So I'm kind of like getting back into it. But what's neat is, like, it fills in so much for you. So it's like, you know, it tells you, like, the name, because there's these little pieces of debug information still in that library. So you can see what's going on in PTC start cycle with callbacks. You know, it calls enable run and standby. It calls enable PTC. And then, like, okay, here's, like, some register maybe that it's writing to. You know, I should look up what this one is, the E000. And this is going to be well, actually, no, this might be a like, it's ORing a value off of something. But, you know, figuring out, like, here, you know, clearing out flags, and, you know, enable EOC int, right? Enable EOC, what's EOC? Like, end of conversion, probably, int interrupt. So this will tell me, if I go to this, it'll tell me what's that interrupt flag. Okay, so this is, like, this almost exactly the same as disable and enable PTC. We're still going to that register 4200 4C00, except in this case, we are turning on so the two upper bits, the upper bit and then middle low bit, and you know, why you need to, right, but usually, you know, again, I would look at the I2S or something. There's usually, if you're clearing a flag, you have to write to, like, a protection flag, and then you can only write them at the same time. So I'd figure out what these are, and then I would kind of, like, see if I can map out what the registers are. And then, you know, I would basically, what would be really neat that I don't believe I can do is if I could write my own versions of all these functions, right? So, like, there's dozens of these little mini functions, clear EOC int flag, which I'm, like, so grateful that they made into a function instead of turning into a macro, because I actually have a shot of, like, doing, you know, if it was a macro, like, I would never be able to know what this is. It would be like, well, you have to set this bit. I don't know what it does, but now it tells me, because it's in the Occam's razor, right? It's in the name. It would be neat if I could rewrite those in my C code, like in the Atmel Studio. And then if I could force it to link to my versions instead of the library version. And then what I would be able to do is I'd kind of do a like a hollowing out of the library. So if I could pick off all these little, like, I know what this does, but if I could actually rewrite each one so I know that I have that perfect, and I would just keep running the program and making sure that it was all working and there was no side effects with my code as I turned it into C. And then slowly but surely I would kind of build enough of the structure that I could figure out the more complicated functions, because I would know, well, all of the mini functions, the little helpers have been taken care of. But I don't know if I'm going to be able to, I don't think I can get the linker to do that. I think the linker will be like, why do you have two functions with the same name? I hate you, and it'll complain. So what I'll probably just do is start a new C file and just, like, name these all out and just try my best to rewrite the code. I mean, this is pretty easy. This is like, 2 lines of C code. And just do one at a time until I get them all done. So that's my plan. If anyone has any other ideas for this plan, let me know, because this is the best plan I got right now.
Okay. Well, everyone's just hanging out, chatting.
That's cool.
All right.
Well, I'd like to see some owls.
Yeah, so that's it for tonight. We'll probably keep broadcasting during the week. Want to,
You want to give away some owls?
No. Yeah, we'll,
No, there's no owl giveaway.
No, that's good.
Okay.
40 minutes. All right, well, thanks, everyone.
Send in your favorite decompiler disassembler
Yeah.
for ARM thumb assembly. If you got one, I'll take it.
I was filming on Saturday, so the camera that I use for me is in a bag. So that's why I'm
That's
just...
okay.
That's why I'm just a talking head
You're
tonight.
just in both.
However,
That's fine.
I am willing to show my handiwork. So on Saturday, while Ladyada was filming a Circuit Playground, I was doing some film tests with Minerva. So this was just fun playing around. Minerva is our owl that helps people learn. Anyways, so that's it. I'm going to play that out. All right. Buy some electronics at adafruit.com.
Yay!
Yeah, that's what pays for these skills.
These skills and these software tools.
And
We like
these
to pay
bills.
people for their software.
Yeah.
It's true. I do.
All right.
I'm the one. I'm the one who does it.
Yeah.